Hello everyone, TS De Lange here. Today I have a very special limit for you. I will show you the Greek limit I designed last autumn for Wadim Zudilin's Limit Beauty contest at my university. It consists of as many mathematically relevant letters from the Greek alphabet as I could find. All of these letters, except alpha and eta, have a properly defined mathematical meaning. Before I show you the limit, I will briefly explain the meaning of each of these letters. Alpha is the variable over which the limit is taken. Eta is a variable we will iterate over. The first mathematical letter is the uppercase gamma. This is the gamma function. It is an analytical continuation of the factorial of x minus 1. Up next is the lowercase zeta. This represents the Riemann zeta function, which is the infinite series of 1 over n to the power of x. We use mu for the Mobius function, which is defined to be 1 for n equal 1, minus 1 to the kth power if n is the product of k distinct primes, and 0 if n is divisible by a square bigger than 1. The next Greek letter we use appears in both upper and lowercase forms. It is the most famous mathematical constant in this limit, pi. Its lowercase is the constant we know and love, and its uppercase represents an iterated product like this. The uppercase sigma, which is our next Greek letter, represents iteration as well. This is an iterated sum. We also use its lowercase form to represent the sum of positive divisors function, which sums up every positive divisor of n. Related to the sigma function is the tau function, which is also called the divisor function, which counts the divisors of n. The next letter we use is lowercase phi for the golden ratio. And our last Greek letter is its closest cousin, psi, which is equal to minus 1 over phi. We do use phi in another context as well, to represent the Euler-Tangent function, which counts the coprime of n. Sadly, we do have to use some non-Greek symbols to make our limit make sense. To limit our Latin, this limit only has two numbers, 1 and 2, and one Latin phrase, lim. Well then, let's see what the limit looks like. It may look a little overwhelming now, but this is all going to change once we get to computing. We can first notice that quite a lot of elements in the limit are constants. Let's first compute these constants. Sigma of 21 is 32. Gamma of 12 is 11 factorial. Mu of 11 is minus 1. Tau of 22 is 4. Zeta of 2 is pi squared over 6, the answer to the basal problem. Phi of 21 is 12. We use this twice. Gamma of 12 is 11 factorial again. And finally, sigma of 11 is 12. For now, we'll leave phi and psi as they are, as this allows us to use some identities involving them later in the limit. Now, let's reduce this fraction a bit. And up next comes one of the most important steps of this limit. We pull the exponentiation of the power out of the limit statement, which lands the base encapsulated in a logarithm within the limit statement. Let's first make this a little prettier, and then we can make a substitution to further simplify the limit. We take beta to be alpha subtracted by phi. This way, our iterated product will look a lot more manageable. Our logarithm does not look any better, but we will fix this later. We can also change the limit statement now, because as alpha approaches phi, beta will approach 0. Now, let's take a closer look at the denominator of our limit. We can prove that this expression belongs to an interesting little O-class as beta goes to 0. In fact, this holds even if we replace 12 with any natural n. We will prove this using induction. For the induction base, we can simply rewrite the singular terms in the sum and product like this. For the induction hypothesis, we will just slightly rewrite the lemma and assume it holds for k. Now, we will prove from this hypothesis that the lemma holds for k plus 1. We first multiply by k plus 1 plus beta to make the product go up to k plus 1. We can now distribute the product on the right side, just like this. In this new expression, we can merge all the terms which belong to little o of beta. By the definition of the factorial, we know that the first term is equal to the factorial of k plus 1. Similarly, the second term is the same factorial divided by k plus 1 times beta. In the third term, we can move k plus 1 into the sum, and then turn this numerator into k plus 1 factorial too, such that we can merge the second term into the sum. Would you look at that? We have now arrived at the hypothesis for k plus 1. This means that every part of the induction proof is finished. Hooray! Now let's use this lemma in our limit. Here we can replace the previous denominator with this new one. And our limit now looks like this. If we shuffle some things around, we can see that the two sums are exactly the same. We can therefore remove this both in the numerator and in the denominator, where O of beta remains the same while it is scaled. Now let's clean up the logarithm. If we shuffle things around, we get expressions on which we can let loose some identities regarding phi and psi. These are those identities. The second is the characteristic equation for phi, slightly altered, while the first is based on the expressions for solutions of this equation. Let's substitute these now. And then we can shuffle things around some more. Then we can use this formula for the little o class of the logarithm. Of course, after we apply it to our situation and rewrite it such that all of the O of beta terms are merged. Then we can finally substitute and rewrite it a bit again. And we can finish it off with a final substitution using our first identity. Now the limit is entirely comprehensible, so sit back and enjoy as we complete the final steps. We end up with e to the power of 20. And if we write this out, it's akin to the sound anyone who does not know Greek would make if they saw this limit for the first time. Thanks for watching!